we present neural cellular automata model and its applications to designing self-organizing systems for solving a variety of tasks. Generally speaking, differentiable self-organizing system consists of a neural controller that is shared by a population of agents interacting on a simulated environment during a limited time span. The whole system is evaluated against an objective function that measures the proximity of the current behavior to the desired. End-to-end differentiability allows propagation of the objective gradient to the controller, steering the system behavior towards the target specification. Neural CA operates on a uniform grid. The state of each cell is represented by a number of real values, 3 of which are visible as RGB color channels. Cells iteratively update their state using the information collected from their 3x3 neighborhood. That cell's perception also depends on a per-cell orientation vector. Smooth manipulation of those orientations allows texture projection on an arbitrarily rotated vector field. In our first experiment, we trained a number of cellular automata models to grow and persist various predefined patterns, trying to mimic the development and regeneration of a multicellular organism. In the next experiment, we used the VGG network-based texture synthesis loss. We trained cellular automata that produce textures similar to the provided examples. The objective doesn't enforce pattern stability, so the proposed method happens to turn static images into living textures. We can also use feature channel activations of the pre-trained Inception network as a guiding signal. Cellular automata becomes yet another differentiable image parameterization for feature visualization. Feature channels reveal a plethora of interesting patterns and behaviors. Regular structures tend to produce particularly interesting behaviors, trying to establish global order from local interactions. In this experiment, we combined 2 different cellular automata rules on the same grid. The boundary region executes a weighted combination of those 2 rules. We observe the capability of related CAs to produce a smooth transition regions, where patterns seeded by one rule continue into another. We call rules related if one of them is a fine-tuned version of another, or if they share a common ancestor. In the next experiment, we train the neural CA model for MNIST digits classification. Only cells belonging to the digit participate in the computation, and the cells are only allowed to communicate with their immediate neighbors. Our training protocol ensures that cells reconsider their decision in an aligned fashion if the pattern gets altered. In the last experiment, we trained the model to mimic the behavior of a particle system. The objective function penalizes the per-pixel difference between the CA-generated pattern and the rendering produced by the physical simulation. The details of the neural cellular automata model are available in our Growing Cellular Automata article at distill.pub. The subsequent experiments shown here will be covered in the upcoming publications. Thank you for your attention.